Hello everyone. Welcome back to another exciting physics session. Let's start with something you've definitely experienced, a metal jar lid stuck so tight that no one in the house can open it. You dip it in hot water, and suddenly it opens like magic. That, my friends, is thermal expansion. When a material is heated, its atoms vibrate faster and push a little farther apart from each other. It's like people in a crowded bus moving to get more space when the temperature rises. This increase in average atomic spacing causes the material to expand. When cooled, the atoms slow down and come closer, leading to contraction. Every substance, solid, liquid, or gas, expands when heated, but not equally. Solids expand the least because their atoms are tightly packed, liquids expand more, and gases expand the most because their molecules already have large gaps between them. As shown in the diagram, when temperature increases, the atoms move further apart and the material's dimensions increase. So next time your jar lid opens easily after heating, remember, it's not strength, it's science. Now let's understand how this expansion happens in different dimensions. If a solid rod is heated, it can expand in one direction, along its length, in two directions, across its surface area, or in all three directions throughout its volume. These are called linear, areal, and volumetric expansions respectively. For small temperature changes, the fractional increase in dimension is directly proportional to the temperature change. We express this using three equations. For linear expansion, we say delta L divided by L equals alpha sub L multiplied by delta T. Here, delta L is the change in length in meters, L is the original length in meters, alpha sub L is the coefficient of linear expansion in per Kelvin, and delta T is the change in temperature in Kelvin. For area expansion, we write delta A divided by A equals alpha sub A multiplied by delta T, where alpha sub A is the coefficient of areal expansion. And for volume expansion, delta V divided by V equals alpha sub V multiplied by delta T, where alpha sub V is the coefficient of volumetric expansion. For solids that expand equally in all directions, we have simple relationships alpha sub V equals 3 times alpha sub L and alpha sub A equals 2 times alpha sub L. In short, expansion is just the same molecular story told in 1, 2, or 3 dimensions. Now, not all materials expand equally. The rate of expansion depends on the bonding between atoms and the internal structure of the material. Metals, for instance, expand much more than glass or ceramics because metallic bonds are relatively weaker. Let's look at a few values. For copper, the coefficient of linear expansion, that's alpha sub L, is 1.7 times 10 to the power of minus 5 per Kelvin. For glass, alpha sub L is only 0.32 times 10 to the power of minus 5 per Kelvin. Liquids expand even more than solids. For alcohol, the coefficient of volumetric expansion, alpha sub V, is 1.1 times 10 to the power of minus 3 per Kelvin. For mercury, it's 1.82 times 10 to the power of minus 4 per Kelvin. And then we have the hero alloy invar, which expands so little it's almost negligible, alpha sub V equals 2 times 10 to the power of minus 6 per Kelvin. That's why invar is used in precision devices like pendulum clocks and scientific instruments, where even a tiny bit of expansion would cause big errors. So, the rule is simple: strong bonds mean small expansion, weak bonds mean big expansion. Now comes a surprise: water does not follow the normal rule. Most substances expand when heated, but water is the rebel of physics. Between 0 degrees Celsius and 4 degrees Celsius, it does the opposite, it contracts on heating. At 4 degrees Celsius, water reaches its minimum volume and maximum density. Above 4 degrees, it behaves normally again, expanding with temperature. This is called the anomalous expansion of water. Why is this so important? Because it's nature's life-saving trick. When a pond or lake cools in winter, the water on top becomes colder and denser until it reaches 4 degrees Celsius and sinks. But as it cools further below 4 degrees, it becomes lighter and stays on top, eventually forming ice. That means the water at the bottom remains at 4 degrees Celsius unfrozen, keeping fish and aquatic plants alive through harsh winters. In the graph shown, you'll see two curves, one showing volume decreasing from 0 to 4 degrees Celsius, and the other showing density peaking at 4 degrees Celsius. So, water's strange behavior literally supports life, quite the overachiever, isn't it? Let's solve a practical engineering problem to see how expansion helps in real life. An iron ring has an inner diameter, written as L1, equal to 5.231 meters. It needs to fit tightly over a wooden wheel rim of diameter, written as L2, equal to 5.243 meters. Both start at a temperature, written as T1, equal to 27 degrees Celsius. We need to find the temperature, written as T2, to which the ring should be heated so that it just fits. We use the linear expansion formula, L2 equals L1 multiplied by open bracket 1 plus alpha sub L times delta T close bracket. Now substitute the values. 5.243 equals 5.231 multiplied by open bracket 1 plus 1.2 times 10 to the power minus 5 multiplied by open bracket t to minus 27 close bracket. Simplify that equation step by step, and we find that T2 equals 218 degrees Celsius. That means the ring must be heated to 218 degrees Celsius to fit the rim. As shown in the diagram, the expanded ring is placed over the wheel while hot, and as it cools, it contracts and grips the wheel firmly, no bolts or glue needed. This is the same principle used in railway engineering to mount steel tires onto train wheels. Physics in action, quite literally rolling down the tracks. Alright, let's tie it all together. Thermal expansion happens because atoms vibrate faster and push farther apart as temperature increases. This leads to linear, areal, and volumetric expansion, measured by coefficients alpha sub L, alpha sub A, and alpha sub V respectively. For solids that expand equally in all directions, we have the simple relation alpha sub V equals 3 times alpha sub L. Liquids and gases expand much more than solids because their molecules are freer to move. Water is the famous exception, contracting on heating between 0 and 4 degrees Celsius. And beyond nature, engineers use the same principle to their advantage, from fitting metal rings to bridge joints and railway lines designed with expansion gaps. So next time you see railway tracks expand in summer or a thermometer rise in your hand, remember, it's the invisible dance of atoms expressing their heat. I hope this session warmed your curiosity and cooled your confusion. See you in the next class, where we'll explore how heat flows from one object to another. Until then, stay cool, but keep your concepts hot.